Okay, welcome back to another Physical Sciences 3 lecture. We're starting on page 8 and we are looking at kinematics. Okay, so kinematics is the study of motion without considering the forces required to produce the motion. We can describe the motion using words, graphs, or equations, so mathematics. Details of the quantities we will use to describe this motion are shown in the table below, and we've already started to use some of these quantities in examples. So distance and displacement, for example. We have a scalar here. Distance is a scalar, displacement is the vector. We represent distance with the symbol d, whereas we represent displacement with the symbol s. They both have the same units, so meters. An example of distance is 45.2 meters. An example of displacement is 500 meters up. And just notice that we have this direction in here. We need a direction because for distance is just simply the number of meters travelled by a moving object, which we're used to. The displacement is the straight line distance and direction from a starting point to a current location. Okay, so that's the key difference there. And we have a nice little picture down the bottom here. Just scroll through some of the other ones. So distance versus displacement. So let's imagine that we're travelling from this point, so this is our start point here, to our finishing point here. Call that the end point. Okay, we start here and end here. So we might have some people that have to drive their car and they have to follow the road. So they're going to have this distance along here. Whereas if we had someone that was able to travel in a helicopter in a straight line, fly there, they'd go to here. Now both their displacements would be equal, so they'd be the same distance from the start point at their end point. However, the distance they travel to get there would be different. So obviously if you're traveling in a car, the road around here is going to take you longer. It's going to be a further distance than if you were able to just fly there from there to there. So that's the difference between distance and displacement. Some of our other quantities we have speed and velocity. So again, these are similar to distance and displacement. They have the same units. So speed and velocity have the same units. They're both measured in meters per second. And this is the scalar and this is the vector. We represent speed just with the word speed and velocity with a v. So this is the rate of change of difference and represented with this equation there. This is the rate of change of displacement and it's there. So velocity relates to displacement and speed relates to distance. Okay, and again, we have for velocity, we have a direction there compared to no direction for speed. We also have acceleration, which is the rate of change of velocity, so how fast something moves up or how quickly something accelerates. I was going to use the word accelerate to describe acceleration, which is a no-no. So basically, how quickly does something get up to speed is acceleration. And time is measured in seconds here. And there are 86,400 seconds in a day. And that's what the definition of a second was from 1884 until the last century. In the 20th century, there were improved methods. Until now, we have seconds defined as the frequency of a cesium-133, which is using an atomic clock. So you don't have to understand this part, but it's just interesting to know that we now have a very precise way of measuring a standard second. And just to go over this one. So this is meters per second squared, or meters per second per second. You can say that a couple of ways. Okay, and we'll look at them in more detail as we go. Okay, you might have noticed that in those equations there was this symbol here, and we call that the delta symbol. It's actually the Greek letter delta. It's capital delta and stands for change in something. So this one here is the change in time. So how much time has passed, essentially. Change in a given quantity is defined as the final value minus the initial value. So the difference between the final value and the initial value. So change in time is we have a final time and we subtract the initial time, and we can represent it this way as well. So we have little subscripts, TF and TI. They are just to signify that we have the final time minus the initial time there. Okay, so in other words, delta T represents a time period, not a moment in time. Similarly, change in V or delta V represents a change in velocity and not a specific velocity. So we use it for average velocity, not instantaneous velocity. Okay. So the table above tells us that velocity is the rate of change of displacement. However, there are two cases to consider. Instantaneous velocity is the velocity at a moment in time. So we might be looking at a car or anything that's moving, and we might say right at that moment it's traveling at, I don't know, 100 kilometers an hour north or something, and is given by the gradient of a displacement time graph. So we'll look at these later on in the course, some displacement time graphs. Average velocity here is the velocity over a time period, delta t, and is given by v average. So rather than looking at the instantaneous time, so at a moment when a car is traveling, we might look at how long it's taken a car to travel an entire trip, and then say, well, it was average velocity was so on and so forth over the whole trip, over the whole journey. We have a sample problem here to illustrate the difference between average speed and average velocity. So an athlete runs 400 meters around an oval track in 50 seconds. Calculate his displacement and distance covered. Okay, so we'll actually start off with distance covered. So distance covered is pretty obvious. If they've run if it's a 400 meter track and they've done one lap, then they've run 400 meters. That's pretty obvious. The displacement here is 0, and that's because they have started and finished at the same point. So they might have, wherever they started their race from, they finished at the same point, and so they have a vector of 0 magnitude. Okay, and when it's 0, we don't need a direction. There's no direction specified, because if it's just 0 meters, they haven't moved, or they've finished in the same spot as where they started. So when we look at average velocity, remember that average velocity is equal to displacement over time. Displacement over time. So if its average displacement is 0, then its velocity is also 0 meters per second, even though they have moved within those 50 seconds. So the average speed is equal to distance over time. So with the average speed, even though their displacement was 0, they did move a distance, which is 400 meters over 50, and so their average speed was actually 8 meters per second. Okay. And we have another sample problem here. So a cyclist is traveling at 7 meters per second east when she speeds up to 13 meters per second east in 4 seconds. So calculate her change in velocity and then her acceleration. So define east as positive, and then we have our final velocity here. So this was our initial velocity. So I stands for initial. So initial velocity, that is equal to VF, which equals final velocity. Alright, and so we have the final velocity here, 13 meters per second, minus 6, is that right? Initial velocity, I think they've made a bit of a typo here. This is actually 7, and that one's 6. Okay, so they've made a little bit of a typo. So it's actually, the final velocity here is 7 meters a second, so the actual speed is 6 meters a second, and then if we change this to equal to, rather than that one's going to be 6 divided by 4. That one's not right, is it? So let's get that out. I think it's going to be 1.33. So if we go 6 divided by 4, 1.5, what am I talking about? So it's actually 1.5 meters per second east. is the acceleration. So it's a bit of a typo there. So the change in velocity was equal to this one, divided by time, 4. So it's actually 1.5 meters per second squared east. Okay, so if there are any more typos throughout the book, just let me know through email. That'd be very helpful. We have some examples here, and I'll put them in the next video.